Today we're going to talk about energy, and in particular chemical energy. Generally, energy falls into a couple of different types. We have potential energy, which is a stored energy, an energy that can be used later on. And when you're at high school, you probably learn about gravitational potential energy. So if this was a cliff and this is a rock, it's got potential energy, and you calculate that using mass times the gravity times the height. You know that when that rock comes over the edge of the cliff, it's going to speed up, and that will give it kinetic energy, which is a second type of energy. There are other types of stored energy, such as a spring energy, if you compress a spring. But another type of stored energy is this chemical potential energy. And so that's energy that's really stored in the bonds of the compounds. So if you have, say, gasoline, for example, within those molecules is energy, and when you ignite it, you break bonds, and it reacts with oxygen and forms products such as carbon dioxide and water, and maybe a bit of carbon monoxide and things, and remaking those bonds with the various oxygen molecules releases heat. Okay, and so again, we could turn that chemical potential energy into kinetic energy. And so in the case of a vehicle, that gasoline ignites in a cylinder and pushes down a piston and causes motion of the car. But even aside from that, if you just heat something up, you get the molecules moving faster and faster, and that's a form of kinetic energy, is the molecular motion. Units of energy, according to the SI units, we have joules. Calories are commonly used, particularly in the United States. Calories are a major unit of energy. The calorie is actually defined as the energy required to heat 1 gram of water to increase its temperature by 1 degrees Celsius. And the amount of energy to do that is 4.184 joules, and we define that as 1 calorie. So say if I have 1 gram of water and it's sitting at 21 degrees, the amount of heat I need to put in to get that 1 gram of water to increase its temperature to 21 degrees, so from 20 to 21 degrees, that would be 4.184 joules. And commonly on the back of your food items and stuff like that, it'll list calories. It's really talking about kilocalories, and so a kilocalorie is 1 cal, but this is a cal with a capital C. So you notice that it's not that little c. So when you're reading on the back of your Mars bar or something and it tells you how many calories it has, it's really referring to kilocalories. And most of the time they'll probably have a capital C, but sometimes they don't. But it's always referring to kilocalories. And so obviously, kilo meaning 1,000 means that we're going to have 4,184 joules rather than 4.184. And this is equal to 4.184 kilojoules. And so as I just said, when food items listed calories, they're really talking about kilocalories. Let's have a look at some energy in food. So protein typically has 4 calories per gram, so 4 kilocalories with the C with the big C with the calories. Carbohydrate again 4 kilocalories, and fat 9 kilocalories per gram. So let's have a look at the energy in the bonding. When you break chemical bonds, it's going to require energy. So if you can think of, say, two atoms that are sort of bound together like this, if you want to separate those atoms, you're going to have to put in energy to cleave that bond, and so then it'll break. Basically, what happens is the atoms get so excited, that they're so excited that they just sort of rip apart. But you've got to put the energy in to give them that excitation. So that's an endothermic process. So it requires energy. If you're going to make chemical bonds, so if you have 2 atoms like this and you try and make chemical bonds, if they're moving very quickly, it's going to be hard to get them to form a bond. And so what has to happen is if they're going to form that bond, as soon as they do, a lot of their kinetic energy has to slow down. And so the only way that's possible is if energy is released from this newly formed molecule. So when we make chemical bonds, we have to release that energy, and so it's an exothermic process. So endothermic means energy goes in, exothermic means energy is released. The way to remember this is the X part is the same as exhale, okay, or exhaust. You know, it means that it's a final thing. It's something that's releasing something. They're hopefully pretty easy to remember. Usually endothermic means that heat will have to be absorbed, and exothermic means that heat is released. So if we have a look at an example with say a hydrogen and a chlorine coming together to form hydrogen chloride, the heat released is 103 kilocalories per mole. So the delta H is given as minus 103 kilocalories per mole. The negative sign means that it's exothermic. It means that heat is released. So if you did this reaction, you would expect that the surroundings would get hotter. So the beaker, well, maybe not, wouldn't happen in the beaker, but whatever vessel it's in would get hotter from this reaction. So always remember that exothermic is a negative delta H, and endothermic is a positive delta H. Let's have a look at the factors that go into this chemical bonding. A lot of it has to do with the bond length, which is correlated with the bond strength. So stronger bonds are usually shorter bonds. So if you have a short, tight bond, it's going to be stronger. Smaller atoms give shorter, stronger bonds. So the smaller the atom, the stronger the bond is going to be. So we have a look at an example here. If you compare hydrogen fluoride with hydrogen chloride, you'll see that hydrogen fluoride has a delta H of plus 136. That means that's how much energy I would have to put in to cleave that bond. So it's 136 kilocalories per mole. To cleave the hydrogen chlorine bond would have to be 103 kilocalories per mole. Notice how this is the positive of the sheet we had just before. And that's saying that if I'm going to break this bond, I'm going to have to put in 103 kilocalories per mole. The energy is always conserved. So if these atoms coming together to form a bond releases 103 kilocalories per mole, then to break that bond, I'm going to have to put in 103 kilocalories per mole. But if you look on the periodic table, you can see that we have in group 17 fluorine, chlorine, bromine, iodine. So as you go down, as long as you're sort of comparing like to like, so if this was hydrogen fluoride versus hydrogen chloride versus hydrogen bromide versus hydrogen iodide, this hydrogen iodide would be the weakest bond, and it would have the smallest energy requirement to break that bond. Okay. Well, you can also do this with ionic compounds, and so if you compared, say, sodium to potassium to rubidium to cesium, if they're all, say, chlorides, for instance, or bromides or something, then the greatest bonding energy, and when we talk about ionic compounds, we usually call it lattice energy, but the greatest lattice energy would be with the lithium chloride rather than all the way down to cesium, because the lithium's so small, and so it's going to form a tight, close bond with that chloride. So if you just to refresh, atomic size increases down a group, but it decreases across a group. So as you go across a period, as you go across a period from left to right, the size actually decreases. But as you go down a group, your size increases. Okay, so let's consider a reaction with methane and oxygen to give carbon dioxide and water. The delta H for that is minus 213 kilocalories per mole. So this is an exothermic reaction. It means that if you ignite methane and oxygen, then you're going to get heat released. And so this reaction releases heat, but this is only possible if the exothermic processes dominate the endothermic. Okay. What does that mean? It means that the bonds formed must be stronger than the bonds broken. So if you look previously, the only way this reaction is possible is if all of these carbon and hydrogen bonds break and form. Let's have a quick look here. So methane actually looks like this. So it's CH4 like that. O2, which you should know from your Lewis structures we've done so far, looks like that with a double bond. CO2 is actually going to look like this. And our water is going to look like this. And so in order for this reaction to proceed, we need to cleave these carbon-hydrogen bonds. We need to cleave the oxygen bonds. Okay? And then what's going to happen is that these oxygens are going to react to give us our carbon dioxide and our water. And so what we're saying is that these bonds here must be stronger, at least as a whole picture, that the bonds that are formed in the products must be stronger, or at least must release more energy than it took to put in energy to cleave these bonds. Okay, so just to give some rough numbers, which is not really accurate, but just an example. Say it took 400 kilocalories per mole to cleave all these bonds. That's how much you had to put in. So say, for instance, it took 400 kilocalories per mole, and this released 613 kilojoules per mole, then you'd have the total, which would be minus 213 kilocalories per mole. So you would have 400 kilocalories per mole, and then plus minus 613 kilocalories per mole, and that would give us minus 213. Now these numbers I just made up. You can find the numbers that's readily available with thermodynamic data, but I just made them up. But that's an example saying that the sum of the energy had to put in, so this would have been a plus value I had to put in to break these bonds, and the energy released when these bonds formed sums to give this. And so back to our postulates here, is that the bonds formed must be stronger than the bonds broken. Okay, that way that the bonds formed are releasing more heat, okay, than the heat that was put in to break the original bonds. Also, it means that the products are lower in energy compared to the reactants. Okay, so because it's lower in energy, it's more stable. So once you form these products here, it's not going to go back, at least not under the same conditions. So if you've got methane and you ignited it with a cigarette lighter in the presence of oxygen, you'll get these products. Now, if at some time later you try and use a cigarette lighter with these two together, they're not going to go backwards, because this is energetically more stable. If it was to go backwards, you would have to add 213 kilocalories per mole, and that's unlikely to happen. There is another property that dictates how this works, and that's entropy, but we're not going to cover that in this course. Okay, so let's have a look at some molar calculations. So in this example, we have glucose. Glucose is going to give 2 molecules of this C2H6O and 2 molecules of CO2. So that's the overall reaction. And we're told that the enthalpy for that reaction is minus 16 kilocalories per mole. How many kilocalories are released from 6 moles of glucose. So if we look at the equation, we've got the stoichiometry is 1 mole of glucose gives this much. So it's automatic to assume that 6 moles of glucose would give you 6 times this enthalpy. And that is the case. And so what you want to do first, though, is verify that you have the right ratio. So I used the glucose given, which would be how much the question's saying you've got. And this is N for number of moles. And then you've got the number of moles of glucose from the stoichiometry. Okay. And so you compare that ratio with 6 to 1. Because it's 6 moles given, and it's 1 here in the stoichiometry. So that's 6. So I know it is going to be 6 times this value. And so I work out delta H. For the 6 moles, it's just going to be 6 times the minus 16 kilocalories per mole. Gives us minus 96 kilocalories. B is how many kilocalories are released from 20 grams of glucose. So now we don't know the number of moles. So we've got to work out the number of moles first before we can do that calculation. Because that minus 16 is on a kilocalorie per mole basis. We need to know the number of moles first. So work out number of moles equals mass over molar mass. 20 grams over 180.2 gives us 0.111 mole. Again, you'd leave this value on your calculator because it goes to some more significant figures. Delta H is going to equal 20.0 grams. Sorry, delta H for 20.0 grams is going to be this number of moles multiplied by our delta H, and you'll see that the mole, the kilocalorie per mole, that mole and that mole and that per mole will cancel, and so we'll have minus 1.8 kilocalories. So let's have a look at another example where the stoichiometries aren't as nice. So in this example, we have basically this is a combustion of hydrogen gas. This would be the exact same thing that happens in one of your space rockets when they're launching from the Earth. They've got hydrogen and oxygen cylinders, and they squirt out those two, and they mix and ignite. And we'd have a delta H of minus 483.6 kilojoules per mole. So these units are different than what we had before. Before it was kilocalories per mole. Now we're working with kilojoules per mole. Okay. If you divided this number by 4.184, you'd be back to kilocalories per mole. What is delta H when 3 moles of H2 reacts? So in this case, we're going to be careful because we've got, it's really 2 moles of this is going to give this delta H. And so we're asked what 3 moles is going to do. And so you should be able to see that you have 1.5 times that number. But let's look at a concrete way of working that out. So again, I use this idea of looking at the number of moles of H2 given. So that's how much we've got to work with, given in the question. And then I look at the number of moles of H2 from the stoichiometry. So I've got 3 over 2, because the stoichiometry here is 2 for the H2. Okay. And so for the delta H for the 3 moles is going to be the 3 on 2 times the 483.6 kilojoules per mole. And yeah, you could look at this in a number of different ways. One other way you could look at it is, instead of looking at, you could do like a unitary method, and so you could say, okay, 2 moles gives this number, so then 1 mole is going to give half that number, and so then you'd be in terms of delta H for 1 mole if you divide this by 2. Then you say, well, the question's asking for 3 moles, so I'd have 3 times this number on 2, if that makes sense. It's probably less confusing if you just follow these methods. But after you work with them a few times, it'll make sense. It'll become easy to work with. And so we work that out, and we get minus 725.4 kilojoules per mole, but we've got to consider our significant figures. And so we have minus 7.3 by 2 kilojoules per mole. This 2 here doesn't count as a significant figure. This isn't one significant figure because this is an exact number. If you remember when we discussed exact numbers, because it's the stoichiometric ratio, this is exact. Okay, this is exact. It's not a significant figure. But the 3 is, so we stick with this. 3.0 is. So we stick with our 2 significant figures here. Okay. The final thing we need to look at is our energy diagrams. And basically, you start off with reactants. Reaction coordinate is the x-axis and energy is the y-axis. The reaction coordinate just means how a reaction is proceeding. You could sort of equivalent to time, I guess, with the time scale of the reaction proceeding. And you start off with reactants. So there'll be reactants at some energy level. So if we're looking at the combustion of methane, for instance, this will be an exothermic one. You would start off with some level where the methane is in terms of energy, and then you would light that cigarette lighter. When you do that, you are supplying another amount of energy. Okay, so ordinarily, if you have say gasoline, or in our case methane or something, and you have it mixed with oxygen, it just doesn't spontaneously, react. It needs some input of energy to get it going in the first place. That's our activation energy. Okay, so when I light that lighter or that spark or something, that gives a few molecules in the area an extra jolt of energy, and so it gives them that extra jolt of energy, and so suddenly your CH4, which is methane, and your O2 molecules are excited, and then they react, okay, and then they form the products. Now in the case of methane, it's an exothermic reaction, so as we stated, the products are going to be lower in energy than the reactants. They're going to be lower in energy, and so the change in the enthalpy is going to be negative, okay, which means that it's exothermic. And I might just draw arrowheads for that so it doesn't look like it's a subtraction. So the negative delta H is going to be an exothermic reaction. If you had another reaction where the reactants that are a certain energy level, you put in your activation energy, and then you form products, but say the temperature goes down, then your delta H is positive. If you had a decrease in temperature, it would be a positive delta H. The reason being is that the surrounding temperature has cooled down because the reaction has absorbed some of the heat. Okay, so in the case of an exothermic reaction, the outside temperature has heated up. So if you burn gasoline, for instance, it obviously releases a lot of heat. Okay, and so that's an exothermic because it means that the heat's being released. Even though we have an increase in temperature, it means that it's a negative delta H because the heat that has gone into surrounding the reaction in whether it's a reaction vessel or the atmosphere or something, that heating of the outside atmosphere has only occurred because the reactants of the products in the reaction have on the whole lost that energy. Okay, you can't get energy from nowhere. So if the outside's heating up, it must mean that the inside, if you like, the reaction must have lost the energy. You can't get something for nothing. Okay, so if we look at an endothermic reaction again, you've got this activation energy still has to be supplied, but now our products are at a higher energy level than our reactants. So in all these situations, delta H is defined as the enthalpy of the final situation take away the enthalpy of the initial situation. So in our case, that's delta H of the products take away delta H of the reactants. Okay, so the other thing is that these activation energy is always defined as the energy supplied from this base value. So you notice that when I'm drawing this activation energy arrow, it's always defined from the reactants where they start at to the top of that hump that has to be supplied. Okay, in both cases. Okay, and again, the delta H, it's defined as the difference between the products and the reactants. So when I'm drawing my arrow, it's going to be between the products and the reactants. Likewise with the exothermic case, it's between where the products have ended up versus where the reactants were. Okay. Now you should be able to see this as a negative value anyway from a mathematics point of view, because if we look at the products, take away the reactants, this energy, I'm not sure what it is, but let's say it's 10, okay, and then after we go through everything, it ends up being 5. Then the difference is the products are 5, take away the reactants, which were 10, so 5 minus 10 would be a minus 5, and so it's a negative value. Okay, so whenever you're drawing an exothermic curve, it should look something like this. When you're drawing an endothermic curve, it should look something like this. And in each case, the activation energy is defined from the initial reactants. You never ever define the activation energy from, say, this bottom part. You never do that, because the energy, the activation energy, was supplied from the start of the reaction, and that's where the reactants are. So I hope that helped with energy, and that's all I'll have for today. Thank you.